So the natural logarithm function, we will introduce that function today. The natural log function is motivated by the question, what is the antiderivative of 1 over x? And so, that's a function we still haven't written down what the antiderivative for is. And so we will actually construct an answer. So we will create a function, and the whole reason the function will be created is so that it can be, the antiderivative of 1 over x. So this function is called the natural logarithm function here. So we define the natural logarithmic function to be, first of all, we introduce notation. So here, ln of x is just some notation we've introduced. Instead of f of x, we're now going to use ln of x, and that'll be fixed notation. And so that notation is defined to be this definite integral from 1 to x of 1 over t dt for each x greater than 0. So, this is the part where we should remember and think about what we're looking at here. So remember here, the only variable would be the letter x here. So x is the only variable on the left-hand side and the right-hand side. And remember that the letter t here is not really a variable. It's a placeholder. It's the variable of integration. We could use any letter there other than x, and we wouldn't change the definition at all. And remember what the definite integral is doing. Here, the natural log has a geometric interpretation. So when we see ln of x, it's not just some random function. It represents this area. The ln of x will represent the area between 1 and x, under the function 1 over t. Now, I do want to point out that it is possible for the natural log of x to be negative. If I pick an x value that's to the left of 1, then when we integrate from 1 to this smaller number, because we've changed directions, the ln of that value will be negative. So it's possible for the ln to be positive or negative. And as I mentioned, the main reason we've created the natural log function is because of this fundamental theorem of calculus part 1, which now says the derivative of the natural log, which is the derivative of this integral defined function, and we know the derivative and the integral cancel, gives us back 1 over x. And so that's really the main reason. The main reason is so now we can say, aha, we now have an antiderivative of 1 over x. I'm not going to say it's the most general antiderivative. We still have some work to do before we could say what's the most general. There are other functions, I'll show you in a second, whose derivative is equal to 1 over x that aren't necessarily identically equal to natural log of x. So I'll show you in 1 second. But the whole reason we created this weird function was so that we can now answer this question. So we now know, the antiderivative of 1 over, so ln of x is an antiderivative of 1 over x. So the derivative of ln of x is 1 over x. So, one question that might come up is, hey, why are we just doing this with 1 over t? Can't we do this with any continuous function? For example, if we're given a function little f, we're asked to find its antiderivative. Why can't we just say, okay, well, let's define a function called capital F that's basically capital F of x will be the integral of little f from some constant a to x. Then by fundamental theorem of calculus, capital F prime will equal little x. And so the question is, why can't we do this with any continuous function? Well, we can. I mean, this would theoretically be the answer to every antiderivative question if the integrand were continuous. So of course, the only reason you can't do this on test is because I'm telling you you can't do it. In theory, this would be correct. But in our calculus class, we want to integrate as much as possible, if possible, and these types of tricks aren't allowed. Well, they're technically correct. So yeah, so we have this new function called natural log of x. And here's this important thing about the natural log of x. It's not a polynomial. It's not a trigonometric function. It's not a root function. We now have a brand new function in our family of functions. And so that's kind of, remarkable. Like we've added a whole new layer of functions. And so now Calc 1 starts all over again. What do I mean by that? Well, if we have a new function, we now have to figure out what's the graph, what are the limits, what's the derivative, what's the antiderivative. We have to learn all the calculus information about this new function. So for example, the natural log function is a continuous function because it's differentiable. Differentiability implies continuity. It's an increasing function because when we take the derivative is 1 over x, but x has to be greater than 0. So the derivative is always positive. So the function is an increasing function. Its graph always goes up as we go to the right, from left to right. And so if its graph always goes up, it satisfies the horizontal line test. And so the natural log function is also 1 to 1. So that means it has an inverse, and so the inverse we'll talk about next time will be the exponential function, which again is a whole new class of functions. So here at the end of calculus, we're really discovering some major functions that, are going to play a big role in differential equations. So one fact we can get right away without doing much work is that the natural log of 1 has to equal 0. Because by definition, the natural log of 1 would be the integral from 1 to 1. And now if you remember for our Riemann sum, in our Riemann sum, delta x is always defined as b minus a over n. In this case, the b and the a are the same. They're both equal to 1. So in this case, my delta x is always 0. No matter if I'm using the left endpoint or the right endpoint or the midpoint, the delta x that I multiply my Riemann sum by will always be 0. The integral is always equal to 0. So right off the bat, we get, one value we found, natural log of 1 equals 0. For the other values of the natural log, note that we can approximate or find the value of this definite integral using Riemann sums. Here the nice thing to appreciate is that we've done everything from scratch. Here, starting out with the area of rectangles and Riemann sums, by taking the limit, we created the definite integral, and then from the definite integral, we've created the natural log function. So we've done everything, from scratch, and we can say this is a bona fide input-output machine. You give me an x value, I'll find the limit of the Riemann sums and find that value, and that'll be the output. So we have a bona fide function, and so now we have to kind of learn all the properties of the function. So by using Riemann sums, we can find values in plot points and sketch the graph. So here's the graph that we see here. The domain, as we said, is x is greater than 0. The range is minus infinity to infinity. As I mentioned, the natural log function can be negative if you pick x to be less than 1. Here, if x is greater than 1, the natural log will be positive, and if x is between 0 and 1, the natural log will be negative. This is exactly what we mentioned. If you pick an x less than 1, then the integral changes direction, and we get a minus sign. Here, the natural log of x as x approaches a equals ln of a. This is just another way to say the natural log is continuous. Because remember, continuity is really a limit property. So if we want to find limits using the natural log, we can just plug the number in. And if that makes sense, then we're in business. As x goes to infinity, the natural log equals plus infinity. This is because the derivative is always positive and it's a forever increasing function. So it blows up to infinity. X goes to 0 from the right, the natural log goes to negative infinity. And here we have a vertical asymptote at x equal to 0. We can officially define the number e, which is the Euler number, to be the number such that when we integrate 1 over t, so if I integrate 1 over t from 1 to e, this is the number where if we integrate, the area is exactly 1. So here, if we think about the graphical definition of the natural log, so the graphical definition says, okay, I've got 1 over t, and now I'm integrating from 1 to any number. For example, if we integrate from 1 to 2, using Riemann sums, we can show this area here is less than 1. If we integrate from 1 to 3, again, using Riemann sums, we can show the area under the curve is actually bigger than 1. And so now we can kind of, integrate from 1 to 2.5 and see what the area is. There you can show the area will be less than 1. And so integrate 1 to 2.6. And so by doing intricate Riemann sums, we can eventually find the number e. It's a number between 2 and 3. It's approximately 2.7. So we give it a special name because this will play a role. The number e will play a big role in finding the inverse of the function, which we'll talk about next time. So yeah, e has this actual geometric definition. If you go back to this graphical definition here, let me get rid of the x down here. If I integrate up to the number e, then by definition, this area under here between 1 and e under the function 1 over t, this area will equal exactly 1. So from the logarithmic function, we can define the Euler number, and then from the Euler number, we'll define the exponential function e to the x, which I'll mention next time. So we have some really important properties of the natural log that we have to memorize. The natural log of a times x equals natural log of a plus natural log of x for any a and x in the domain of the natural log. And the natural log of x raised to the r equals r times ln of x. So you can bring that exponent down and out of the natural log, and that's a really important property. And then finally here we have the natural log of the quotient a divided by x is the natural log of a minus the natural log of x. And then I mentioned this one, it's just a special case. Here, the natural log of x to the minus 1 is equal to the minus ln of x. It's just a special case of ln of x to the r equals r ln of x, where r is negative 1. These properties here are super important, and one of the reasons all of these properties are one of the reasons we really like the natural log function. And we will use these properties all the time. So let me do a limit problem. We're starting calculus all over again, so let's do some limit problems. Here, this is the limit of the natural log of x squared plus 1 over x squared. Here, the important thing to remember is that we have continuity. The book describes continuity this way, that the limit of f of x, in this case, f of x is ln of x, the limit of ln of x as x goes to a equals ln of a. I like to also keep in mind that a itself actually is a limit. I like to think of a as the limit of x as x approaches a. So really, at the end of the day, continuity allows us to bring the limit inside the function, inside the natural log function. And so that's what essentially I'm going to do here. Here we're going to take the limit, bring it inside, and then reset. Now we're doing a new problem. So now the question is, what's the limit of x squared plus 1 over x squared as x goes to infinity? If you plug in, we get infinity over infinity. So we use dominance of powers. Here it's x squared over x squared, or 1. So I get the answer is, natural log of 1 here, which is 0. So it's just kind of taking, the fact that the natural log is a continuous function makes doing limits with the natural log pretty straightforward. It's very similar to when we did limits before, except now you might have to bring your limit inside the natural log. So this limit problem is a little tricky. So let's evaluate the limit of sine of x over natural log squared of x as x goes to infinity. So here it's really important just to realize, and this is something that we need to learn in Calc 1, that sine of x as x goes to infinity by itself does not exist as a limit. It oscillates forever. So this limit sine of x over ln squared of x as x goes to infinity is indeterminate because we don't know what the numerator is doing. The numerator oscillates forever. So here we have to try some other limit techniques. We need to do further math. And here the trick will be to use a squeeze theorem. Because for sine of x, we know we can bound it. And so we're hoping we can use the fact that it's bounded in a squeeze theorem. So one notational comment, I do want you to be very careful. Here, ln squared of x is not the same as this ln squared of x is not the same as ln of x squared, which would then be equal to 2 ln of x. Ln of x squared, that's ln of x times x. Here, ln squared of x, this is ln of x times ln of x. The square's on the outside. Okay, so be careful with the notation. So as I mentioned, we'll use a squeeze theorem. And here, one thing I make the comment that as x goes to infinity, since x is going to infinity, we can assume x is greater than 1. And why do I need to make that comment? Mainly, I'm worried about the denominator being equal to 0. I know the natural log will equal 0 if x equals 1. So here, I'm just pointing out to myself, since we have a fraction, that I know for this fraction, the denominator is not 0. Since x is greater than 1, because x is going to plus infinity. So it's kind of a small technical reason that you wouldn't comment that you wouldn't necessarily have to worry about. But this is now the heart of the squeeze theorem argument. Sine is between -1 and 1. Let's multiply through by 1 over ln squared of x. Ln squared of x is not going to be negative because it's squared. So the inequalities don't change their directions. And now we take the limit. The limit satisfies the inequalities. And now we're going to calculate these limits at the end here using dominance of powers. So how does that work? As x goes to infinity, ln of x goes to infinity. So ln squared of x goes to infinity. So here we get 1 over infinity in limit, which is 0. And that's true for both limits. And so the limit of sine of x over ln squared as x goes to infinity equals 0 by the squeeze theorem. I just wanted to remind you of a squeeze theorem argument as we're starting to end the semester. It's important. Squeeze theorem shows up in Calc 2, so it's always important for us to be able to do a squeeze theorem. So here I wanted to prove these properties, ln of ax equals ln of a plus ln of x. You don't need to know the proof. And maybe I should skip this, but anyway, I hate to just give you a formula and ask you to memorize it without somehow motivating it. So this will be a good practice of our U substitution. Here we prove the identity just by manipulating the integral. Okay, so first and foremost, remember the definition of ln of ax. Just in general, the definition of ln of blah is equal to integral 1 to blah of 1 over t dt. So here, ln of ax, by definition, the integral will be the integral from 1 to ax, 1 over t dt. Now, we use properties of the integral, write 1 over the integral from 1 to ax as the integral from 1 to a plus the integral from a to x. So here we go from 1 to a, and then a to x. That's the same as going from 1 to ax. So 1 to a to x, a to ax, excuse me. That's the same as going from 1 to ax. So if you look, actually, this integral here, ln of 1 over a, 1 over t dt, that's actually the definition of ln of a. by definition, ln of a would be integral 1 to a 1 over t dt, since ln of x is integral 1 to x 1 over t dt. So we've got half of what we're looking for. I'm now going to show you by doing a u substitution, I can make this other integral look like ln of x. So that's what I'm going to show you now. So here, if we use the following u substitution, u equal to t minus a. So, the question is, how did I know to use u equal to t minus a? I played around with it a lot and kind of did a lot of scratch paper and messed around with it till I figured out what worked. Okay, and I'm just showing you what works and not the things I tried that didn't work. I also kind of knew where I was headed, so anyway, if we let u equal t over a, be very careful. T is a variable, u is a function of t, but here a is a fixed constant, okay? So yeah, in my integral, I have the expression t. So let me solve this for t. So here, t equals a times u. So when I change the integral from the t variable to the u variable, I'm going to replace this t right here with a times u. And the other thing I need to solve for is dt. And so here, if I take the derivative of both sides, keep in mind a is a constant. I get dt equals a times du. And then the final thing I need to do is to convert the bounds. These are in terms of the letter t. I need them to be in terms of the letter u. So I can plug in t equal to a right here. And so when t equals a, u equals 1. And when t equals ax, u equals ax over a, or just x. And so I've written that down right here, the change of boundary. So now we're ready to completely convert the integral. So here, I just wanted to be a little explicit, so I wrote t equals just so we know what bounds we're in. And so now I'm going to convert this thing. The bounds will change to 1 to x. The t down here, I'm going to replace with a times u. And the dt, I'm going to replace with a times du. And here, when I replace everything, we notice that we can do an algebraic cancellation here. So notice this is dt, this is t, and these are our new bounds in the u variable. So it's completely converted, and now I notice the constant a can be canceled. So we end up with the integral 1 to x, 1 over u du. Remember, u is a dummy variable here. This u doesn't matter. You can change this to any letter. This could be 1 to x, 1 over t dt. So in fact, this integral is the definition of the natural log. ln of x is equal to definite integral 1 to x of 1 over, t dt, or any dummy variable other than x. 1 over blah, d blah, whatever, any variable other than x. And so we can put it all together. ln of a the x, I can write as the sum of integrals, and the second integral here, by doing the u substitution, we can write it as 1 over x, 1 over u du, and so that gives us ln of a plus ln of x, if you go back to the actual definition. Like I said, you don't need to know the proof, but you do need to know the property, okay? And here you can use a similar technique. If you use the substitution u equal to the rth root of t, you can prove this property, starting with the integral definition of ln of x to the r, which would be the integral from 1 to x to the r of 1 over t dt. Anyway, you can play around with that if you wish. Let me prove this ln, the quotient rule here, well, not quotient rule, the ln of a divided by x equals ln of a minus ln of x, the natural log, the rule for the natural log for a quotient. This is really a quick proof. Here, ln of a, I'm going to write it as ln of a times x over x. And then I'm going to move this denominator to be under the a. I'm going to write this as ln of a over x times x. And now I'm going to use this property here, that the natural log of the product is equal to the natural log of the first term in the product plus the natural log of the second term. So I'm going to write this as a sum ln of a over x plus ln of x. And then to finish the proof, I'm going to move the ln of x to the other side. So it's kind of a sneaky proof. And, I had to play around with it a little bit before I figured it out. This was not at all obvious. I had to play around with it before I finally figured it out. I don't show you the scratch paper. I don't show you the stuff that doesn't work. I don't show you, me trying to figure out me getting stuck and then me trying again. You don't see that part. I just show you the stuff that works, but that's all part of the procedure. Trying it, getting stuck. Anyway, you don't need to know the proofs. You do need to know these natural log properties. So let's finally talk about the derivative here. So the whole reason we defined this natural log function is so that we now can conclude by the fundamental theorem of calculus that the derivative of ln of x is 1 over x. And another way to say that is an antiderivative of 1 over x would be ln of x. So here's the chain rule version. So here, I'm taking the derivative of ln of some other function of x. And so what you should see here is a composition. The very innermost function is this function u of x, that's the inside function. And the ln of x part, that's the outside function. And so for my chain rule, I'm going to do derivative of the outside times derivative of the inside. So derivative of ln of blah is 1 over blah. So here, derivative of the outside gives me 1 over ux. Derivative of ln is 1 over times the derivative of the inside. And the inside is u, the derivative of the inside would be u prime. And so we can combine them into a single fraction. So here the derivative of ln of u of x is u prime over u by a chain rule. So these are new derivative rules that we now need to memorize. So we have to add this as a new differentiation rule to our list of derivatives. So here's an example. I wanted to do the derivative of ln of a constant times x. So here, this is a composition of functions. The inside function is a very simple function. It's just c times x. So here, when I use a chain rule, I do derivative of the outside. Derivative of ln is 1 over, right? Derivative of ln of x is 1 over x. So here, derivative of ln, the outside gives me 1 over cx, where c times x is the inside function. And so now I'm multiplying by the derivative of the inside. C is a constant, x is our variable, so the derivative of c times x is just c. And now the constants cancel. And we see that the derivative of ln of cx is 1 over x. That is to say, we found another antiderivative. So it's interesting. We went from not knowing the antiderivative of 1 over x at all to now having 2 antiderivatives. We have too many. But in this case, we can actually use the properties of our log, of the log function, to kind of get out of this mess. Here, using properties of the log, we can write ln of c times x as ln of c plus ln of x. And if c is a constant, then the ln of c will also be a constant. So here, this function really just looks like the natural log of x plus some constant. So ln of cx is actually still in the same family of antiderivatives. It really does just look like ln of x plus a constant. It's just been written in a different form. This is similar to, we had done a problem with, I think it was secant squared tangent, where we got the antiderivative was secant squared over 2, and we got it was tangent squared over 2. And there's no discrepancy there because those functions differ from each other by a constant. And we have the same thing here, essentially. ln of cx and ln of x just basically differ by a constant. So they're in the same antiderivative family. So we're still trying to find the most general antiderivative. So we haven't answered that question yet, but we're getting close, and I'll answer it shortly. So here's another derivative problem. the derivative of the natural log of x squared plus 1. You should identify it as a derivative problem. Note that it's a natural log and that this is a composition, that the x squared plus 1 is inside the natural log. And so I need a chain rule. And for the derivative of the outside, the derivative of natural log is 1 over its argument, So here, for the derivative of the outside, derivative ln of x squared plus 1 would be 1 over x squared plus 1 times, now I want the derivative of the inside. The derivative of the inside is x squared plus 1. The derivative of x squared plus 1 is 2x. So now I multiply 2x times x squared plus 1. I get 2x over x squared plus 1. Just to practice the notation, the new derivative formula, and of course, always the algebra. So, this is a new formula that you have to add to your list. And, at the end of the semester, it's easy to get tired, but we have to find our second wind and finish strong. That's really important now. I know, easier said than done. And I don't know if I'm trying to convince you or me. So here's another chain rule problem. Find the derivative of ln of secant plus tan. This one is kind of interesting, so I just kind of want to show it to you. It's kind of fun. So here again, it's a composition. Secant plus tan is the inside function. So derivative of ln of u is u prime over u. So here, this secant plus tan is our function u. So I have u prime over u. Now, this is a sum, so I can distribute the derivative to each term. The derivative of secant, I hope you remember, is secant tan. The derivative of tangent, I hope you remember, is secant squared. So here I get secant tan plus secant squared over secant plus tan. And then, our algebra vision kicks in. We notice that secant is a common term. So I factor out one copy of secant in the numerator. And so I get secant times quantity tangent x plus secant x. But that's exactly the same as what we have in the denominator. So I can cancel the tangent x plus secant x with the secant plus tan, and we get back just secant. So here we've learned that the derivative of ln of secant plus tan equals secant. Another way to say that is the antiderivative of secant is ln of secant plus tan plus c. So this example also tells us what the antiderivative of secant is. So the antiderivative of secant, this is a fact that you will learn formally in Calc 2. But I just wanted to show you this derivative problem, does show us what the antiderivative of secant is. So this derivative problem here, I wanted to just, give you some notation to think about. So here it's a little bit tricky. We've got the cube, and then we've got the square, and it's important to understand that they're in different places. The cube is outside of the natural log. So here, when I say ln cubed, that's ln of whatever times ln of whatever times ln of whatever. That's the ln is being cubed. And the x squared, that's inside. So that's ln of x times x. So here, ln cubed of x squared would be ln of x times x times ln of x times x times ln of x times x. That's what this notation represents. So if I'm going to take a derivative, it's important to understand that we have a composition, that the inside function is this ln of x squared business. And the outside function is blah cubed. It's something cubed, where the something is ln of x squared. So first I want to do the derivative of the outside, the derivative of something cubed. You bring the 3 down and you subtract 1 from the exponent. So here is my derivative of the outside function. I brought the 3 down, subtracted 1 from the exponent. That's where this square comes from. Times the derivative of ln of x squared. Again, ln of x squared is a composition. It's ln of a function where the function is x squared. So the derivative here will be u over u prime. So here's my derivative of the natural log part. The derivative of ln, the outside would be 1 over x squared times the derivative of the inside is 2x, and then 2x times 1 over x squared. So sorry, here's the derivative of the ln of x squared. And then we combine everything, multiply all the numerator terms. 2x times 3 is 6x times the ln squared x squared divided by this x squared term in the denominator. So this example is really about the notation and you sort of carefully looking at the notation and working through it. And here there's a composition of basically three functions. The x squared is inside the natural log, and that's inside a cube function. So this example will answer the question finally, what's the most general antiderivative of 1 over x? And also we get to do something with absolute values. So it's asked us to find the derivative of y equal to the natural log of absolute value of x, and also sketch the graph. So remember, for the absolute value of x, we should use the definition. Remember that the absolute value of x equals x if x is greater than 0. Here we usually write x greater than or equal to, but in this case, if x is equal to 0, the function is undefined. So I've listed that as a separate case because of the domain restriction. For natural log, x has to be greater than 0. And the absolute value of x will equal negative x if x is less than 0. So I've just applied the definition of the absolute value, where the absolute value gets replaced with x if x is greater than 0, gets replaced with the negative x if x is less than 0. In this particular case, the function is undefined if x is equal to 0. So there, we're just not going to include that case. And so, most books may not even write this part where I said it's undefined if x equals 0, but I wanted to be very explicit and so that we didn't, miss anything. But yeah, so now I can take a derivative. Now that I know what this function looks like, I know that this notation here is actually this. So now to take the derivative of this left-hand side, I'm just going to go in and take the derivative here on the right-hand side, where the function makes sense. So where it's undefined, I'm not going to do this. So this derivative, I'll just take the derivative of that and take the derivative of ln of negative x. Derivative of ln of x, no problem. That's 1 over x. We know that. Derivative of ln of negative x, you should see a composition of functions. The minus x is inside the natural log. So I need a chain rule. U is negative x. So u prime is minus 1 divided by minus x. Remember, the derivative of ln of blah is 1 over blah. Here the ones cancel, and we get back 1 over x. The ones cancel. So the derivative of the ln of absolute value of x, regardless if x is greater than 0 or if x is less than 0, the derivative is always 1 over x. By the way, be careful. Remember, negative x is not a negative number. Just because a variable has a negative symbol in front of it does not mean it's negative. You need to know that we need to know the domain of x. Here, x is less than 0. So if I put a minus sign in front of the x, it'll be a positive number. So here, the negative x is actually positive. So yeah, so we conclude that the domain is all reals except 0, and that the derivative of the natural log of absolute value of x is 1 over x. Here's the graph where I'm just using a reflection to graph ln of minus x. Remember, you replace the x with a minus x, it reflects about the y-axis. I said we're repeating Calc 1, you're going all the way back, even to these graph translations. And ln of absolute value of x, we now define formally as the most general antiderivative of 1 over x is the ln of absolute value of x. Okay, so this is a new antiderivative formula that you have to memorize. And the absolute value part is very important. So now, we have a new rule. So quick example. So here, anti-definite interval from -3 to -2 of 1 over x dx. So here, just for fun, think about the picture. Here's 1 over x, the graph of 1 over x. We're integrating from -3 to -2 So we're trying to find the net area of this region. So we're expecting the answer here to be negative, okay? Because you see the orientations below the x-axis. I'm integrating from -3 to -2. I'm expecting the answer to be negative. Okay, so let's see what happens. For the antiderivative, I'm using the most general antiderivative, ln of absolute value of x. Now I'm doing f of b minus f of a. Absolute value of -2 is just 2. Absolute value of 3 is just 3. So here this becomes ln of 2 minus ln of 3. And then I use the property of logs. So ln of 2 minus ln of 3 is ln of 2/3. And this is a negative number because 2/3 is less than 1. If you think about the graph of the natural log, it's really important to always keep the graph of the natural log in mind. You'll see 2/3 would be right here. And we'd get a negative answer. So here, using the absolute value is really important. If I didn't have absolute values here, the natural log would not even be defined because I'd be trying to take the natural log of a negative number. And I go, uh-oh, something's wrong. You know, so the absolute value is crucial. Here's another one that involves a U sub. So it's really important, you know, I recognize it's an integration problem. Then I just say, is this one that I just know off the top of my head, or we just have a formula for? The answer is no. So now I need to use some techniques. In Calc 1, the only other thing left to do is use substitution. And so now I'm looking for patterns. Is there any part of the integrand that's a derivative of the other? So, you know, you might have noticed here, there's an x squared minus 25, and there's a 2x, and certainly 2x would be the derivative of x squared or x squared minus 25. Here we let u equal x squared minus 25. We try to get as much mileage out of our u substitution. So here I can get rid of x squared and the minus 25 by letting it equal to u. That's what I'm going to do. So I make a difference of 2 terms into 1 single term. That makes the problem simpler, hopefully, because there's less, you know, terms involved. So let u equal x squared minus 25. Then don't forget the dx. That's the only thing. When doing a u substitution, don't forget to convert the integral completely. So here du would be 2x dx. And in this case, we have everything we need to convert the integral. So I moved the 2x over so that it's next to the dx. And now the 2x dx I'll replace with du. And the x squared minus 25 in the denominator I replace with u. So I get antiderivative of 1 over u du. And now I can use, that's exactly this pattern here. I can antiderivative of 1 over blah d blah equals the natural log of the absolute value of blah. So here, antiderivative 1 over du is the natural log of the absolute value of u plus c. Very last step, plug back in for u, because the original problem was in terms of x, so I want my answer in terms of x. And again, the absolute values are important. Just for the natural log function here to be defined, it is possible for x squared minus 25 to be negative, you know, so. Yeah, so we've got this new antiderivative rule to mention, to memorize, and don't forget here the absolute value part is really important. So 2 more integrals, and then I want to talk about logarithmic differentiation. We'll see how much time I have. 2 more integrals here. Here's what we haven't done. We never talked about the integral of tangent. So here, this would be, you know, something that's fair for this class. So first, remember, tangent is sine over cosine. And now we're going to do a u substitution. I'm going to let the denominator be u. I'm going to let cosine be equal to u. Then du is minus sine dx, which is good because I'll get a sine dx in the numerator. And when I replace tangent with its definition, I get a sine dx in the numerator. Yeah, it's missing a negative symbol, but that's okay. I can multiply a minus sign on the inside and the outside just to balance that out. And so now I can completely convert this negative sine dx into a du. And so my integral now looks like negative antiderivative 1 over u du. Remember, the cosine x in the denominator becomes a u. And we know now the antiderivative of 1 over u du would be ln of absolute value of u, and I plug back in for u, which is a cosine. So I have minus ln of cosine x plus c. And you could stop here. Most calculus textbooks go one step further. They bring the minus sign using the properties. So remember, we know ln of x raised to the r is equal to r times ln of x. So here the r is a -1. And we've used the property backwards. So read this equation this way, from right to left. We took the r and we brought it inside and put it up. So this minus sign, we took it inside and brought it up. And so most textbooks list the antiderivative of tangent as the natural log of 1 over cosine, or secant, the natural log of the absolute value, of secant, and then plus c. So this would be a problem, that's fair game for Calc 1. And this is how we find the antiderivative of tangent. We need this natural log. Here's one last u substitution, and then I'll talk about logarithmic differentiation just a little bit and stop probably. So here, again, we're looking for patterns, so here it's really important now that you learn the derivative rule, and I've seen this problem many times. So I know, the trick is if you let ln of x equal u, then du is 1 over x. And by, quote unquote coincidence, I have exactly 1 over x times dx, i.e. dx over x in my integral. So here I write ln of x over x is ln of x times 1 over x dx. I replace ln of x with u. 1 over x dx gets replaced with du. The integral of u is u squared over 2 plus c. Plug back in for u. So I get here, it's 1/2 ln squared of x plus c. Be careful about where that square is. That square is on the outside of the natural log. So, this is kind of a new pattern to look out for. Anytime there's a natural log, and if there's an x in the denominator, making u equal to natural log might be, a good option when doing integration problems. So let me just talk about this slide here and stop, and I'll continue this next time. One very important application of the natural log function is known as logarithmic differentiation. So we motivate logarithmic differentiation, for example, by asking the question, how do I find the derivative of a function that looks like, for example, x raised to the x? So here it's very important to realize we cannot use the power rule. The power rule only works when it's a variable raised to a constant. Here I have a variable raised to a variable. So that's really important that you recognize the difference. Variable raised to a number, no problem, I can use power rule. Variable raised to a variable, hold on. We're going to have to use this thing called logarithmic differentiation. So the idea for logarithmic differentiation is perhaps we can use the properties of the log to make this easier. One really nice property is, as I mentioned, ln of x to the r is equal to r ln of x. So we can bring down the exponent. And here the whole problem is I have a variable in the base, but I also have a variable in the exponent. So maybe by using the properties of log, we can bring that exponent down somehow. So here's the theory of logarithmic differentiation, and I'll start here next time, but let me just go over the steps really quickly. To find the derivative, so I want to find dy dx. To find y prime, to find the derivative of y equal to f of x using a technique called logarithmic differentiation. Here are the steps. Starting from y equal to x, first take the natural log of both sides, starting from y equal to x. Then simplify the right-hand side. So here you'll have the ln of f of x. When we take the natural log of both sides, we'll have the ln of f of x. We want to simplify the ln of f of x, the right-hand side, using properties of the log, such as bringing down the exponent. Then take the derivative of both sides. We will end up using implicit differentiation. I'll show you when we do an example. Take the derivative of both sides, solve for y prime, and that's how logarithmic differentiation works. So I will show you an example and go over this procedure on Friday in great detail. I just want you to now start to really distinguish between when you have a function raised to a function, like x raised to the x, versus when you have a variable raised to a constant, like x raised to the n. For x raised to the n, we would use the power rule. But for function raised to the function, variable raised to the variable, we're always going to use logarithmic differentiation. Okay, so, I'll mention this again next time, but that's kind of one of the big takeaways here, is to really be careful, really pay attention to the form of what you're differentiating. Is it variable raised to a variable, or is it variable raised to a number, or is it a number raised to a variable? And so I'll talk about all that next time. So I'm going to stop right here, folks.